So we're going to finish up chapter 7 today. Hopefully I'll at least get to introduce the next chapter. We're going to be pretty close to that. But my goal is we take the exam on Friday. We're not doing lab on Tuesday. I'll probably spend an hour and a half on the lab time on Tuesday, and we're just going to spend it as like a day of notes. So I want to make sure that we can get through the 8, 9, 10 chapter, and then as we're talking about the stuff in atomic spectroscopy in 8, 9, 10, we're going to go next door and look at instruments so you can see what the actual instruments look like.
So do you believe all of 8?
Yeah. It's only like 60 slides. It'll be easy to do in 3 days. So Monday, Tuesday, Wednesday, just 3 normal lectures. Get through that with no problem. So we're talking about monochrometers in chapter 7, so our wavelength selectors, and we're just kind of finishing this up. The last thing we talked about was resolution of the instruments. You had a clicker question of it, but we talked about how to resolve adjacent peaks and how to calculate that resolution that's required. And the resolution was related to the number of blazes per millimeter and also the order. So that's important to remember that when you go to higher order radiation, that you get to higher resolution of separation. So a lot of times the monochrometers use first order radiation, like the Shimadzu instrument, when it scans, it uses first order. But to really get high resolution separation, you can go up to the 30th order or the 40th order. And I'll show you some examples of that as we go into the next chapters. So the slits, the entrance and exit slits, they play important roles in the instruments. Their goal is to create the rectangular image that is going to be positioned at the focal plane after the wavelength selection. Because of that, the slits should be ideally exactly parallel, so everything's in the same plane, if you want to think of it being a plane in this direction. All right, that's just some alignments. Upper end instruments, they're going to be adjustable. Low end instruments, they're going to be fixed slit width. The Spectronic 20, the 20 and the 20, Spectrum 20 means the 20 nanometer slit width. Okay, so that's the bandwidth that's coming through the instruments. The Shimadzu one's adjustable. You can have these things come in close to only select a very narrow portion of the focal plane, or you can open up wide to get more power. Most commonly, you set them the same on the entrance and exit side. I've never done a measurement where they weren't set the same. There might be a reason, I just don't know why you don't keep them in parallel. The entrance side of the monochrometer, that's what it serves as is an effective light source. So with that, you're controlling power. So power can be increased by opening it up or decreased by narrowing it down. The exit slit lets you isolate that region of the focal plane, so you narrow it down, you get less intensity, but you get higher resolution because the effective bandwidth narrows down. So illustrate that kind of just the trade-off that you've got. So if you can imagine the focal plane's up here, and you've got different colors. So you've got one color and a second color and a third color. And we have to keep in mind, if it's a continuum source, these things are all blended together. So it's not, this ideally is 3 monochromatic beams of light coming in. Well, the continuum sources are not like that. It's continuous. So whenever we think about these settings or adjustments, our trade-off is between getting the intensity we need and the resolution that we want to have. If we want more detail in a spectra, or we're wanting to isolate a single line with atomic emission or absorption, we crunch it down and we use a narrow slit width. All right, so we're going to drive these things inward, and we're going to try to get just to isolate this particular band of radiation that's going to be transmitted to. So separate out from 2 from 3 and 1 from 2. But if we want more power, and if we're trying to do Beer's Law's measurements with quantitation, typically we're trying to maximize the power. There we're going to use the widest slit width. We're going to let the more wavelengths go through to increase the power. It's easier to see a change. This slide kind of shows the different settings side by side, what you'd see. So if you had those three monochromatic beams of radiation that were close to one another coming in. If I go with a wider slit width, all three could pass through, and this would be your effective bandwidth. And I start to narrow it down, so I go a little narrower here. So you can't really see it that unless you get them on top of each other. But it's starting to go in a little bit. So now it's starting to isolate. It recognizes there's three different peaks in there. And then if I crunch it down even further, what would happen now, I could isolate the three different signals from one another. So it just depends on the compound that you're looking at and how far sharp the peaks are, or the components you're looking at. If they're very, very narrow peaks, you're trying to do an analysis of like an atomic spectroscopy, then it's to your advantage to use a very, very narrow slit width. If it's molecular species that have big, broad, 100 nanometer wide peaks, you want more power, so you just open it up. So it's this gives you an example of the spectra. This is benzene. This is benzene vapor, I should say. So benzene C6H6. Because it's so volatile, you can just take and put a drop of it in a cuvette and put a cap on the cuvette, and the vapors from benzene will saturate in the gas phase at plenty high enough concentration. So you're actually doing a gas phase measurement in this, not a liquid phase. But in the gas phase, because the intermolecular interactions are not strong, gas molecules are moving off in a straight line, now your spectra become much, much sharper and more detailed. So here's the same sample, just with example of three different slit widths. So if you open it up to, or narrow it down to 0.5 nanometers, you start to see this fine detail. We call it the hyperfine splitting that occurs. Very, very, if you want to think of it, fingerprint. A lot of detail in there. It's going to be hard for something else to match that exactly. But when you open it up to a 1 nanometer bandwidth, that detail starts to disappear, and you go to a 2 nanometer bandwidth, it's gone completely. And if I were to open it up to a 20 nanometer bandwidth, it would be completely gone. We wouldn't realize that these are even isolated peaks. Okay, so we just have to know what we're looking at to some detail. All right, what do we put our sample in? Well, sample cells, they, number one, have to be transparent at the wavelength of interest. So in visible, we use glass of some form. In the UV, we have to use quartz or fused silica. Fused silica is nothing more than synthetic quartz. Glass will work through the visible up to the near infrared, so you can go to about 2,000 nanometers. There's a few things you use there. We have plastic disposable cuvettes. That way, if you use them once, you don't have to worry about carryover. So they cost 50 cents a piece, something in the neighborhood of 30 to 50 cents, depending on the quantity that you buy. And they look just like a little glass one, except they're plastic. They're not quite as reproducible in terms of the path length, because plastic's going to vary a little bit. But they'll work in all of the visible and down to about 330. So you can't go into the low UV with them. They're polystyrene based. Now the downside with the plastic ones are solvents. So you put something in it like a solvent like DMSO, you'll dissolve the plastic. So you have to be, you can't use acetone, something like that. So they're fine with aqueous. You just have to be careful with those. So I'll show you one of those next time we go into the lab. Aqueous only is typically where we look at those with. If we're going to go and do our analysis up in the infrared, now we're looking at typically using some type of a salt, KBr, sodium chloride. The problem we have with all those compounds is they're water-soluble ionics. So you have to have very dry solvents to use those guys. We can use symmetric polymers in the infrared. They have an absorbance, but because they have so much symmetry, they don't have signals at a lot of different places. So you look at something like a common one is to use Teflon. Teflon has a couple of signals in the IR, but for the most part, it's pretty calm. So you can take and put your compound top this, and you run it as the background, have it subtract out, and it can really make analysis easy. What you do with those is you take your Teflon, and you can actually stretch some Teflon tape out, and where it gets pretty thin, and then you take your sample with the solvent in it, and you put a drop on it. You allow the solvent to evaporate out, and then you're left with just small deposits of the analyte that was in that solution left, but it's enough to get a signal on sometimes. Okay, so last topic in this chapter is radiation detectors. So the goal of the detector is to take the electromagnetic radiation, convert it from the form of light of some form into an electrical signal that we can process and do something with. The earliest detectors that we used were the human eye. We actually have if you go down to the seminar room in 214, look in the shelves over on the left-hand side of the room. There's something that looks something like a microscope. But if you'll take a look at it, it's a color comparator. So the way that it works is you have a reference solution, and then you'd have a solution that you want to measure. So you have a sample and then a reference. And it's got a probe that sticks down in the solution that you're looking in. So light's transmitting through this. And then you've got this reference one that's at a fixed value. And you move this up and down so that the color compares the same. And you're looking at the intensity of the light using your eyes as a judge. And you're just trying to move one side up or down to those two things that match. What you're varying is the path length, but you're making the absorbances match using the path length. Okay, so it's the optically, all the processing is done with your eyes and the brain. So you're just varying the path length. That was the instrument used up to the introduction of modern electronics. That's what we did before the Spec 20 came. Now, all of the wavelength selection had to be done with your eyes, so that was the disadvantage to it. It didn't have any filters whatsoever, but the eyes are fairly sensitive. We get more sensitivity. We can use photographic plates. I told you this earlier. Every chemistry department had a dark room in the day. That was our early way that we detected things. Thankfully, today we've got electronic detectors, and because I have no idea how to develop film, we make a wish list. We want a detector to have high sensitivity, a high signal-to-noise ratio. We would like for it to have a constant response over a very wide range. I want it to respond fast. Ideally, I want it to have a minimal signal without illumination, and this is so it would go through the origin on calibration curve. And I want the output signal, whether it be current, voltage, or whatever I'm measuring, to be directly proportional to the radiant power. That's my wish list of things. And most detectors can do that to some degree. So if we think the signal that we see from the detector, if it's directly proportional to power, this calibration sensitivity is your proportional constant. But almost all detectors have some type of a signal that you see without illumination. We call that the dark current. Okay, so the dark current is the signal present without illumination or electromagnetic radiation. So if you put the detector in the dark, there's still a signal you see. Now this is what we correct with when you do a 0% T. So you're offsetting that signal in electronics when you do a 0% T. You're blocking any light from hitting the detector, and you null that signal out. Okay, so that's the purpose of doing that. Okay, so we're going to talk about a couple of different types of detectors. So here's the definition of dark current on the next page. You offset that dark current with to get 0, and we have detectors that can respond to heat in the IR, but ones in UV vis, they're going to respond to photons. So heat detectors are going to be IR, photons are going to be IR or UV vis. Most of the ones in the IR that respond to photons are really expensive detectors. They're only going to be on your highest end instrument. So one of the oldest detectors that we have is called a vacuum phototube, or a photoemissive tube. I think I got a couple of those. And this dude's pretty simple. Okay. So it's got a semi-cylindrical cathode. Okay, so that's this side of it here. It's got a photoemissive material on it. And it's got an anode that's separated by it, and that's inside of a tube that's got a vacuum pulled on it. So it's evacuated. Now, because of the separation between the cathode and the anode, current can't flow across that. What happens is a photon of light comes in, and when this photon of light strikes the surface, what it does is it causes an electron to be ejected. So a photon of light comes flying in here, it strikes the surface, and an electron is ejected from the surface. When this electron is ejected, it's attracted to the anode. And what's the charge of the anode? Positive or negatively charged? Yeah, anode means it attracts anions. Anions are negatively charged, so this guy is positively charged. So the electrons come flying to this anode, so that gives you a flow of current. So the current flow across this system is directly proportional to the radiant power, the number of photons coming in. Now, one of the things that, because of this separation, if you have something that has a very high resistance, you can hook it up to an operational amplifier, and you can amplify that signal very easily. So this configuration with the operational amplifier is called a current follower, and what it does is takes this current and converts it into a voltage. So it goes current to voltage, and in the process, it amplifies. So where your current flow going across this detector is going to be picoamps to nanoamps, 10 to the minus 12th to 10 to the minus 9th amperes of current, which would be very, very hard to measure. You can multiply it by 1,000,000 times with an operational amplifier, and you can get a signal out of this that's millivolts, which is easy to read. Okay. Now, the different types of detectors are the surfaces on this photocathode respond differently to light. One of the most common ones, and I think both the ones you have, are the 117 photoemiss. Its problem is that it works well in the blues and the 400s, but if you try to do a measure at 650, it's died out. So there's a lot of times, there's some enzymes that you use in biochemistry that you need a 650 measurement. It's near worthless for it. So you can get a more expensive detector. You can get one that's got the 128. It's much more sensitive over a wider range. You got to make sure the surface detects at the wavelength you want to detect. If you want to do something in the near IRs, you can get this this S12, and it's got some sensitivity down here in the IR, but it's not near as sensitive as the other detectors. So there's no one good detector that works for everything in these. And the good thing about this is you don't need high voltage to power it, 90 volts. That's easy to transform up or to come from a wall and run to that. So the cathode emits the light off. You collect those electrons that are emitted. From that, you can amplify those. It's easy to amplify because you've got a big resistance across there. and the current flows directly proportional to the signal. You've got different types of materials that respond to different wavelengths. And we quantify detectors based on their quantum efficiency, the number of electrons they emit out per photon in. Ideally, we'd like to have a detector. Every photon comes in, it kicks an electron out. At best, those detectors that you have are quantum efficiency of about 0.2, 0.3. So they're capturing, yeah, something like that. So they're not ideal, but they're cheap. So if you want to think of why do we use these things, they're cheap. Linear response, low voltage. The disadvantage to them is there's not an internal gain or amplification. They're good for high light situations, but they're not good for low light situations. So for the most part, I'll say old school. There are not many of these being shipped out in instruments today. They've been replaced by something better. So on higher end instruments, and everything that you've used so far has been using a photomultiplier tube. And a photomultiplier tube works very well when you have low light. Okay, so PMTs, photomultiplier tube, we talked about changing the voltage to this on the fluorometer this week in lab. It works well with low radiant radiation. It still has a similar photoemissive cathode. It emits electrons out when it's exposed to light. But now what the tube has is a series of photoemissive anodes, each one we call a dynode, and there's typically 9 of them. And maybe, for example, the first dynode's at 90 volts more positive than the cathode, so the electrons are going to be drawn from the cathode to the first dynode. And as they're drawn, they accelerate. When it hits the first dynode, it kicks in 1 or 2 electrons off, or 2 to 4 electrons off, which are accelerated to the second dynode, which is 90 volts higher. And you repeat that process typically 9 times, and it gives you an amplification in the order of 1 million. What that means is every photon that comes in, 1 million electrons come out, or 10 million electrons come out. And this process is called internal amplification. All right, how's it work? So here's a couple of examples. Oops, there's that one exactly. So I'll let y'all hand these back and forth to look at it. One is one design. The one that Brianna has is an older school design, but with that one you can actually see the resistors laid out in the tube. So the diodes in that one are in a linear fashion. But you see the resistor set up. So when I take this 900 volts from the source, what's happening is it's divided across a series of resistors. So there's 10 resistors in here, and the first diode sees 1/10 of that. So it's got 90 volts. So the second one sees 2/10 of it. So this diode is going to be at 180. And the third one gets 3/10. It'd be at 270, etc. So inside of this part and this guy, all those resistors are shoved down in there. Okay, so here's kind of the idea that what's going on. So light comes in. I definitely want the smallest ink. So radiation comes in. It strikes and emits an electron off. It's attracted to D1. It hits this first dynode, and for every electron that comes in, it ejects 2 to 3 electrons off. And that's the amplification. Now, when it's ejected to dynode 2, because it's the next highest potential, every one of those eject 2 to 3 electrons off. And then every one of those eject 2 to 3 electrons off. And every one of those eject 2 to 3 electrons off. You can see where I'm going here. And finally, at the end, you've got where you collect it at the anode, right? But one photon comes in, and you kick in 1 million to 10 million electrons out. This is the most sensitive detector we have. Okay, so there's some things that we can do to even make them more sensitive. One of the things that we can do is cool them down. So we look at PMTs are commonly used for high-end instruments in the UV vis, where you need high sensitivity. The sensitivity is limited only by the dark current, which you can reduce by cooling it. So if we need high sensitivity detection, we'll take this detector and immerse it in liquid nitrogen or liquid helium. Take it down to 77 kelvins liquid nitrogen, or take it down to liquid helium 4 degrees. So both of these were made by the same company, Hamamatsu. They're the Japanese company, and they pretty much are the only company in the world that makes them. Hamamatsu with an H, H-A-M. So they basically can charge what they want to make these things. They don't make the design like this. They'll give you out of this one. The company that this one went inside of one of my research instruments, and as a UV vis detector, I actually have a couple of them. Here's one that we broke the glass on accidentally, doing work on it. But the company I was, Beckman, who sells the instrument, they were selling this detector for $3,000. Even Hamamatsu was charging them $800, $900 for it. Now, detectors typically will last a while. The problem with this one is that you can damage it. If you have the sensitivity cranked up and you hit it with high radiant power, basically this turns into an electrical torch going on. So you can actually destroy this thing by hitting it with too much light. You have to be careful. So the way, if you're in a high light situation, you just turn the gain down, turn the voltage way down, a couple hundred volts. So it can cause temporary saturation or damage to the surface, or permanent damage to the surface. So it's a consumable in these instruments. The advantage to them is that very sensitive, adjustable amplification. Like we tried with our analysis with the quinine, if we had too much sensitivity at 600 volts, we could turn the detector down to 550, and we could get calibrated scale. The disadvantage to it is that they typically have a high dark current and it's temperature sensitive. Now you've got a power supply that most of them will have an adjustable power supply feeding them that runs up to 1,000 volts. So you're talking about $1,000 for that power supply to get one of high stability. They're useful in low light situations, so it's not an everything detector. Okay, the photodiode. And I used to have a photodiode in my box, and I don't know where it's made its way off to. I don't know if we would steal a photodiode, what we would do with it, because it's not in my box anymore. Yeah. So it's a reverse base PN junction diode, like we talked about diodes earlier. If we think about in the reverse bias, we talked about diodes, and in the forward direction it conducts light or conducts current. In the reverse direction, it doesn't conduct any current until you hit the breakdown voltage. The way that these work is you use it in the reverse bias mode, and you have a depletion layer formed. Okay, so if you think of the N region and the P region, where the light's separated, or the charges are separated from one another, if you change it around, let's see if I've got a picture of that. I do. So if you change it around so that in reverse bias mode, so the negative terminal is hooked to the P side, P region, and the positive terminal is hooked to the N region, the charges all run to the opposite side. So that leaves this layer in the middle called the depletion layer where current can't conduct. And what happens is a photon of light comes in, it strikes this region, so H nu is a photon, and it creates a hole. So it creates a hole, it kicks an electron off, which is free to flow this way, and a positive charge carrier which flows this way, and that gives you the flow of current across the wire. Okay, so that's the way that detector works. We used one of these when we built our little spectrophotometer out of our electronics kit. That was what's on the detector side. Okay. They're not very big in terms of size. They're going to be typically some dope silicate of some region, and they have conductors hit to them. Whenever radiation comes in, it creates a hole in the electron, which provides current in the system, which is directly proportional to power. In terms of sensitivity, they're more sensitive than the old phototubes, and they're less sensitive than PMTs. So they're kind of in the middle. They're fairly broad range sensitivity, but they change a lot with every wavelength. The good thing about them is, like anything in chip-based, they can be mass-produced cheap, so they're you can actually make these things for a few pennies a piece. They're very linear over a wide range of radiated power, 10 orders of magnitude, which is wonderful when you can get that wide. They're tough as nails. I mean, you literally have to break one for it not to work. The disadvantage to it is that every time you change the wavelength, you've got to recalibrate it. Okay, so they're very wavelength sensitive. Even the new Spec 20Ds that we have, the distinction on that name, the ones that we've been using, Spec 20D, that D means that it has a diode-based detector versus an old school phototube. And the good thing about them is they're 1% stability guaranteed for an hour. That means you can calibrate it for an hour, it's good. So that's compared to the old phototubes. The old phototubes, especially, were very temperature sensitive, and you couldn't go 5 minutes, you'd have to recalibrate. I mean, they sucked. You get into doing measurements and doing calibration, and you put in check 100% T that you'd set an hour ago, and it's down at 80%. Like, shit, start over. It was rough. The photodiodes made life better. Now, the good thing about the diodes is that diodes can be put next to each other and used in an array format. So, diode arrays are a linear series of photodiodes placed side by side, and you simply put this array at the focal point. So the instrument that we used with the PKA measurements was a photodiode array. What happens is all the wavelengths are measured simultaneously. So the one that we used had 4,096 diodes side by side, and the good thing about it is that now it allows you to detect all wavelengths simultaneously. So you go into your wavelength separator, and you separate every different wavelength of light. It's going to strike at a different point on the diode. It knows that this is what wavelength it is. This is wavelength 1. This is wavelength 2. This is wavelength 3. It knows where to look in this linear region, and you can see all these things as quick as it can go click, click. You detect all the wavelengths together. In fact, my little toy detector that I use, that's what's inside of this little guy, because it's a photodiode array. So you can really make these things compact, and they're amazingly powerful compared to what we could do even 20 years ago. They're phenomenal. Now, the downside to it is you're not just reading one signal, you're reading 4,000 signals simultaneously. However many diodes there, you have to have the circuitry to read all those different points simultaneously. So the first instrument that I saw that was a photodiode array was a desktop instrument. So it was, let's see, starting graduate school in the late 80s. So it was probably, had a bench space of about 2.5, 30 inches, but next to it were 6 foot of processing electronics. So the instrument itself with the photodiode array was this big, and all the stuff trying to get the information into the computer was huge, because every one of these took its own circuitry in terms of an amplifier, that it took every circuit, it would trap the circuit from the diode with a capacitor, and then flip the switch, and it would integrate how much charge was in that capacitor and give you a signal out of it. Okay, so every one of these places where light would come in, it would be trapped in this diode. You would have to process every one of those things to detect. So literally, you would collect a signal and hit the spectra button, and it would take like 2 minutes to digitize all of it. But that was still quicker than a old school scanning instrument. So today, thankfully, electronics have changed it, so it's instantaneous for all purposes. All right, so where we are today, we've changed our technology even more. And you're very familiar with these, even if you don't know you are. Charge transfer devices are now detectors that use two-dimensional arrays, a series of columns and rows. So transfer devices work much like photographic film in a way that they integrate signal as a function of time. So on an old school film camera, you had something called shutter speed. And that represented how long for the mechanical shutter to open and how to let the light come in. So a normal shutter speed was like a 60th of a second for stills. If you were in a dark situation, so a room wasn't very bright and you still wanted to have vibrant color in the system, you put the camera on a tripod and you could open the shutter up a tenth of a second, or if needed, seconds at a time. And it would let enough light come in that be equivalent to a highlight condition. And you can still get a good image out of it. But if you're doing something like sports or motion, your pictures are going to be blurred. It would be not good. Well, in that same sense where you can vary the exposure time of the film, with charge transfer devices, you can do the same. They store the charges that are created in wells, and then they, at the appropriate time, once you've said, I've looked long enough, what we call the integration time, we read how much charge is there. The most common of these is the one that's in your cell phone, a CCD, charge coupled device, and there's a very similar one. The book uses the terminology charge injection device. They all work the same way. There's minor differences in these things. They have like a diode, have a photodepletion layer where it creates charge. But what they do now is they store the charge and they measure it at time X. So these are pretty simple cartoons of what's going on, but you get the idea. So you've got this pixel. So this little electrode is what today you think of on a camera as a pixel. All right, so this is one pixel. And what it is where there's a positive charge put on one region. So this is a N-doped region, and this is the P-doped side of it. And light comes in, and it strikes and creates a hole. Right? The electron's emitted out, and the electron is drawn to the closest pixel, and the positive charge carrier goes to the other side. But there's a barrier here that's an insulator, and that electron can't flow through. So the electron's drawn to this. Let me use a different color. The electron's drawn to that pixel, this electrode, but it can't cross it because it can't go across that insulator. So there's a barrier here that traps these electrons in what's called a well. So you can store the electrons underneath this well until you've got enough electrons to count. Okay, so we vary that with integration time. So this is how I do astrophotography. I've got a CCD detector, and it's a 16 megapixel camera. And the way that I can see things deep in space with my relatively small telescope, so you can, if you want to see faint lights, you can make your eye bigger. Al sees at night because it's got huge aperture eyes. I have a 14-inch telescope, all right, but I can see images that 30 years ago we saw only with 2-meter telescopes. And why? Because my detector, instead of looking instantaneously, I can take my detector and tell it to look for 5 minutes. Instead of just looking in a moment, I'll collect all this signal up for 5 minutes. All right? Or if that's not enough, if I can track good enough, I'll tell it to look at it for 30 minutes. All right, it's limited by how well I can track the stars. But what happens is every one of these things are going to have a different, if you think about it in a two-dimensional array, every one of these is going to have a certain number of charges trapped in these wells, right? We can create an image. To detect them is the crazy thing. What happens is that you take and you will read the number of electrons in this first well. And then you'll take everything and make them shift over 1. And then you read them. And then you go across this line, read this line, and then you transfer everything up 1. So everything moves up 1. Then you'll read equivalent of this line. And then this line. And this line.
So you really only read one well
at a time. So when you've got a camera that's a 16 megapixel camera, it makes 16 million different readings. And
so on your CCD, if you tell it to watch for 30 minutes, it gives you one picture after 30 minutes.
The one image, yes.
Yeah, not a time lapse of the whole thing.
That's correct. Now, if I want a time lapse, I can just take quicker images. The amazing thing about these things is that each electrode each pixel can store, actually we're at 10 to the 6 now, electrons.
You're saying it only reads that one top right one, or it reads all of them?
It only reads in that top right place.
Okay.
That's the only place where it reads them.
Okay. That's
So what it does is it does charge transfer to shift them from one pixel to the other. So it'll read the ones in the first row and throw them out, and it'll move everything over, and it'll read there again, and then read again, read again, and read again. So those pixels is one position in the array, and you can get 1 million electrons underneath one of those things. The efficiency that they work with is they can transfer an image, and they'll only lose about 5 electrons in 1 million. I mean, it's highly, highly efficient. It's amazing what these things can do. So the advantage of this now, I'm not looking at a one-dimensional array like a photodiode array. I can actually create an image, two-dimensional image. And we're going to see in the next chapter that if we now separate our light in multiple dimensions, we can separate wavelength from order and not ever have to worry about overlap. So there's advantage to this. You can vary the integration time to increase sensitivity. You don't like the signal you got with a second, integrate 5 seconds. You don't like what you got with 5 seconds, integrate 30 seconds. If you've got enough sample, if your sample's being consumed, you can just keep feeding sample in there, but if your sample's not being consumed, you can integrate as long as you want to. Okay, so the disadvantage to it is that there's complexity in the software and the hardware, but today that's been conquered because this is a freaking amazing. I mean, the image your cell phone takes.
Well, just our calculators and stuff.
Yeah, but the processor that drives most cell phones today, you don't know what your cameras are. I'm a 5.6.
I just got a new 8 something plus.
So my guess is that's
it's the one right below the 10.
That's probably at least a 20 megapixel camera.
I don't know.
Yeah. Look at that.
About. I don't know how to work it.
Yeah, I don't know what the.
So is that how, like, you'll see them space pictures? Like, for me, like, look up at night, you don't see this thing. But you can see space pictures where these different, it looks like it's almost pink, or it's just these different colors. So that's coming in over time.
Well,
the human eye doesn't see it.
Yes, and it could, and it couldn't. Let's go one slide, then I'll show you a couple of examples. Here's an example of a signal that needs high resolution separation. So here's the analysis of an atomic emission spectra, and this is some metals thrown in there, but just with a high resolution separation. These are inverse wave numbers. Here's something wavelength we can see, but these is angstroms. So imagine this represents 5 nanometers. Okay, so that's 0.5 nanometers. Sorry. So that's 5 angstroms. That window is 0.5 nanometers in size. sometimes we have to have high resolution systems because when you go to atomic species, the peaks are so sharp. And like iron's got a number of emission lines in this one little tiny region. All right, so there are times we'll see this in the next chapter, where high resolution is an absolute necessity for us. So I'll show you just a couple examples of images that sometimes a lot of the images that you see are created with filters. So AstroPix. These are all images that I've taken. Oh, don't make me.
Okay, so
Are they what?
How many pixel camera? do you have?
1920 by 1080 pixel resolution.
What is it's what now?
It says 1920 by 1080 pixel resolution at 401 ppi.
And my Adobe's expired on this. Let me go into Paint and try to open these things up. Then maybe I can just get them in a viewer. So, like, here's an example of a very faint galaxy. I tried the image. It just, even with, if I looked at this with my eyes and through the 14-inch telescope, I see nothing. This is an immigration over an hour. So this galaxy is 300 plus million light years away from Milky Way. It's way stinking out here. But like this is a true color image. This is what it looked like in space. There are reds and
That's what I was.
yeah, there are colors there, but a lot of times things have been doctored to the point. Like here's a very colorful region. This is the Horsehead Nebula. Okay, they don't have that option. Well,
Did you change your integration just based on the night or based on what you're looking at?
yeah, like on this example, this is called the Horsehead Nebula. So this is the flamed corner of it, but there's a star right here that's blinding me. It's much closer to us, and then the reflections from this star. This is not a UFO I've captured. This is internal reflection inside of the telescope due to the brightness of the star. Yeah, it's just screwing me up. Let's see if I've got planets are boring. So I mean, some of the things have amazing detail associated with them. Like here's the Crab Nebula. I mean, it kind of looks like a crab wrapping around something. That's the actual color associated with it. Like here's Orion. And this is an old image that I took, but just it shows you a good example of color. So, I mean, that's the actual true color. So you look in Orion's belt.
But is that's way closer than.
It's in the Milky Way, so it's not out of our galaxy. Like the Ring Nebula here has a lot of color to it. So you see greens and some faint blues. Now, what we see are based on the elements that are there. So if you think about it, we're seeing the glowing elements that are in the gases. So this example of the Rosetta Nebula is primarily hydrogen gas, and hydrogen glows red, so we see all this red glowing gas. Now, what you see with your colors, your pictures that don't look real, this is with a camera. All my images are what's called one-shot color, just like it uses a CCD, and there's a filter on top of every third one that does a combination of RGB, red, green, blue. And it mixes those colors to make the color that we see. That's the way a TV screen works, and that's the way this works. A lot of people that do high-end astrophotography, they'll use a filter and just do a combination of oxygen. They'll look at the elements that should be in that figure, or in that thing in space, whether it's oxygen or hydrogen, and they'll collect a signal just from those. So they'll use a narrow bandpass filter that only looks at a nanometer or 2 nanometers wide, and now they get rid of all the other junk that's there.
Just get the color they want.
Yes. And then they actually record that with a camera that doesn't see color at all, and then they'll go back and recreate it. They'll stack their images together and recreate. That's a false color image, and some of them are very obvious. There's not all these vibrant greens in space, but there are greens in things like comets. So there, occasionally you'll see a few things, but there's a amazing amount of color that we just can't see it with our eyes that exists in deep space. So just trying to. I've got a.
Never. They offer like an upper level astronomy class.
Yeah, our person that teaches astronomy here doesn't film anything.
Is it
Pancake.
That's cornbread. That's what
Oh.
I had corn. I cooked for.
We cook cornbread pancakes. But
Yeah, that's.
I've never.
Yeah.
Well,
That's,
because it was in a cast iron. That
you
makes
make
it.
cornbread? Yes.
Well, I don't have.
You don't make.
Men don't understand that women need good utensils so then they can cook them.
all right. So there's Orion. Just show you some pictures I took recently. I've got a new small telescope, but it gets higher precision. Looks at a bigger field. So there's Orion I took. That's the Seven Sisters. That's Pleiades. Here's a broader picture. So there's the horse head.
Oh, that's so.
There's the flame.
What's the plane?
Yeah, the yellow. That's the point.
Yeah, this is the Flame Nebula. So this is a active star forming region. This is N33. Like here's Andromeda, and I don't know how to process it well enough. Otherwise, this is so bright in the center it blinds everything else. So I'm blocking the center out, but huge amount of detail that's in that. But yeah, you get some.
That horse head.
Now this one's I don't know. It's hard to see. I need to rotate it. It's called the Running Man. You see him running. This is his head. His arms swinging out. That's his legs.
I need to get the legends. I'll show you all.
Yeah. Yeah. It's there's actually a lot of color up there though. Okay.
My sister was
Have a good weekend.
into the space